Alright, this is LeetCode 102. It's called binary tree level order traversal. So it says given the root of a binary tree, return the level order traversal of its nodes values, right? i.e. from left to right, level by level. So almost like how you read a book, you go left to right, then you go to the next line, you go downwards, right? Okay, so what they want us to do is let's look at this example. So this is the input. So this kind of input represents this binary tree. You can see 3, then the left child is 9, which is this right here. Then the right child is 20. And then to represent that 9 has no children, i.e. it's pointed to null, then this is why that's the case. They put null, but in Python, basically that's none in Python. So as you can see here on the right hand side in the tree node definition of the class, that if you don't provide a left and a right child, then the default value is going to be none or null, which is basically equivalent in Python. Okay, and then this 15 and 7 represents that these are children of this 20 node. Okay, and then what they want us to output is an array of the values in level order. So the array is 3. This is on the first level, right? So this is, you can imagine this being level 1, this is level 1, right? This is why we only have a 3 there. This is level 2. This is level 3, right? This is level 2. So we start from level 1 at the very top of the root node, and we count as we go to a new level. So at level 2, that's why we have 9 and 20 in this subarray. So you can see it's a 2D array, right? It's an array of arrays, basically. And then inside of the subarrays, we have just the node's values. So, and then on the third level, we just have 15 and 17 and 15 and 7. Yeah, so how would we actually do this? Well, if you're familiar with tree traversals, usually there's 2 main ways how to do tree traversal. So there is DFS or depth first search, and then there's BFS. Okay, so DFS stands for depth first search. So you would go as deep as possible. So you would maybe go like 3, then let's go all the way down to the left node, and then we'd go all the way down to this side, then we go to this left node. You can see that if we followed that traversal, if we went like 3 to 9, then 3 to 15, or to 20 to 15, then to 7, we wouldn't get this output that we want, right? A better way would be to use breadth first search. So breadth first search goes basically goes kind of like what we want. It goes level order. So we would start at 3, then we'd go to this next level, and we would start from left to right, and then we just do 9, and then we would add its subchildren to some data structure, and then we would go to the next one, and we would produce this output basically. Breadth first search. So let me just get this out of the way so you don't get confused. So BFS, or breadth first search, utilizes a queue to do its kind of like its traversal, right? So the way that it works is that we're going to utilize this queue, right? And you can import a queue into Python, or you could just use like an array and act it as a queue. So you can act it. Queues are FIFO, right? So first in, first out. Queues are FIFO, meaning that if you think about like in real life, if you ever got into like in line at like a cash register, if you were the first person in line, you're going to be the first person to be attended to, right? So that's what FIFO stands for. The person who's first in line is going to be the first person to get out of that line because they're going to get attended to first. Hope that makes sense. So we're going to use like an array. Let me just draw it this way. We're going to use an array, but it's going to have the FIFO structure, and so it acts like a queue, right? Or you could import a queue, but I'm just going to use the array so we don't have to import any libraries. And so what we're going to do is we're just going to place this into the queue. We're going to append it, and the way that we're going to make this array act like a queue is we're going to append to the end. We're going to append to the end, and then we're going to pop off the front, right? Because you can imagine if this was the front of the line over here, if this is the front of the line where the pencil's at right here, if this is the front of the line and we add to the back of the line, then we want to pop off the front. So we always want to pop off like the 0 index at index 0, right? And then we want to add to the end of the line. This is like, you can imagine this being like the cash register would be over here, and then the queue or the line of people starts it. You don't cut people in line, right? You go to the back of the line. Okay, so we're gonna do while this queue is filled with something, while it still has values in it. What we're gonna do is we're gonna say we're gonna add this node to an output node. So we're gonna have an output kind of, because it's an array of arrays, right? So we're gonna have an output variable, right? That's going to be an array itself, and we're going to append subarrays as we get the values at each level. So at the first iteration, we're only going to have 3, so we're going to append a subarray of 3. But before we remove this from our queue, right? This is our queue. Before we remove this node from our queue, we want to add its children. So we would remove this queue or this value 3, but then we would add its subchildren. So we would add 9 and 20, and we would want to add it, if we want to read it from left to right, then which one do we want to add first in the queue? Well, we want to add the left child first because we want to read left to right, right? So we're going to add 9. This represents the 9 node, and then we're going to add 20 to the right of it. So now 9 is at the front of our line, right? And we've added this 3 as our sub output, and then we're just going to loop through this queue, and we're just going to say we're going to add it as a subarray, and we're going to say these are the new values, 9 and 20. Great. And then 9 does not have children. Its subchildren are just none or null, so we can stop there. And then we'd add 20 subchildren after we remove this, and we just keep going, right? And then eventually we would get another subarray of 15 and 7. Hopefully that kind of makes sense. I think it'll make more sense as I write out the code. So let's go ahead and write it out over to the right. So like I said, we're going to have an output array. Output is equal to just an empty array, and then we're going to have a queue, which is an array as well, but this is going to be we're going to treat it, the operations that we're going to run on it are going to follow the FIFO structure. So we're going to append to the end, which is just using the append function, and then we're going to pop off front, or the 0 index, right? That's going to kind of mimic the structure of a normal queue, or like a line if you think about it in real life. Okay, and then we're going to say we want to add the first element, the root, to our queue. So we're going to say if root does not equal none, then, so if the root is present, because this first root value can equal none, but if it's not equal to none and there's actually a value in there, or if it's a present node, it's not equal to none, then we want to we want to add it to the queue. So queue dot append root, right? Okay, and then we're gonna have a while loop. We're gonna say while q. So while q does not equal none. If you ever see any code that just says while q, it's kind of shorthand, I think, for just saying while q does not equal none. But for the sake of this video, I'll just write while q does not equal none, just to be a little more explicit and so that the code's a little easier to understand. So while q does not equal none, then we're gonna initialize a subarray that we're gonna add to, and we're gonna say for I in range length of the queue. So for however many elements are in this queue at this time, we want to run it. We want this for loop to run, right? So in this instance, when our queue has a 9 and a 20, two nodes in it, this for loop's gonna run 2 times. And what we want to do is we want to pop off the node at the front of the line. So queue.pop. Then we're going to provide 0. Pop is just a function that lets you remove elements from an array and at a specified index. So element or arrays start counting from 0. So this would be the front of the array or the front of the line. And then we're going to say values subarray dot append the node dot value, the node that we just popped off, right? And then before we get rid of this node, before this loop iteration ends and we lose the access to this node, we need to actually append its subchildren. So we need to say if node dot left does not equal none, then we're gonna say queue dot append node dot left, and we're gonna do the same for node dot right. So if node dot right does not equal none, then we're gonna say queue dot append node dot right. Okay, and then at the end of this for loop, we need to not at the end of the actually when we're out of this for loop, we need to add to our output.append whatever this value subarray came out to be. So this is going to have the values of the current nodes in our current iteration of this queue. So we're going to append it to this value subarray so that we have this structure that they want us, right? You can see that this bracket right here, this right bracket, represents an array, and then this left bracket represents the start of the array, and then inside of it we have arrays. We have more arrays, so it's an array of arrays. So we need to basically add to this output a subarray. So we're building it. This for loop is building those subarrays, and then we're appending it at the end. Okay, and then that should do it, and then we can just return output. Let's see if this works. Any mistakes? Taking a little bit. I might have made a mistake. Give me 1 second. Alright, so I spent a little bit of time trying to debug the problem, and apparently, well, the problem was, as you can see before, if we go into the submissions, let me get rid of this stuff over here. We were getting time limit exceeded, so that kind of led me to believing that there was something wrong with the while loop. And as you can see before, the condition was while q does not equal none, right? Apparently, and I actually learned something new today. This is basically saying this doesn't work the same as saying while q. So if we run it with this, while q does not equal none, basically I thought it was the same, but I guess it is actually different. So if we run it like this, then you're going to see it's going to time out, and our solution is not going to be accepted. But if we run it like this, while just saying while q, then it works. So that solution works. Basically, what I think it's saying is that let me actually do some research and confirm this. All right, so I actually did a little bit of kind of some research and stuff, and I figured out that uh, originally I was saying that we would run it as being as a condition saying while q does not equal none, right? The problem with that and the reason why we were getting time limit exceeded was basically our loop was an infinite loop. This condition was never going to evaluate to false. The reason being is that the condition is we intended it to be while the queue still has values, right? The problem is that when the queue is empty, when it's just an empty array, this still evaluates to true. This still evaluates to having like not being equal to none. So um, so this would just keep running forever. However, when we just run it saying while q, this is equivalent to saying while the queue has values in it. So if I exchange what we had it to from saying while q to just saying while length of q does not equal 0, then it still works. Okay, cool. And then hopefully that makes a little sense. Sorry for that little bit of confusion. It was probably good to run into that now instead of having that in an interview. So I wanted to go over the time and space before we end it. The time I believe would be big O of n, and I believe that where n is the amount of nodes in this tree. So imagine, because we have to go through every node in the tree, right? So if there were n nodes in this tree, if there's 5, so if n was equal to 5 in this case, then our time is going to be O of n. So it's going to scale linearly according to the amount of nodes as our input size grows. Okay, and then the space is going to be big O M, and M is going to be the size of our queue, right? So our queue is going to grow, but at its own, the greatest size it's going to be is going to be the size of the greatest level, right? So if this level had, it seems like in this level we have at most 2 values. So at most our queue is going to be of size 2, right? In this scenario right here. So M is going to represent the biggest level, basically the biggest amount of nodes at a single level. So yeah, that's the time and space. Let me know if you have, if you agree or if you think there's some slight alterations to it, but at least we got the code to work, and yeah, thanks for watching.